This is starts chapter 7. It says, as long as chemistry is studied, there will be a periodic table. And even if someday we communicate with another part of the universe, we can be sure that one thing both cultures will have in common is an ordered system of elements that will be instantly recognizable by both intelligent life forms. So there is some thought that the idea that we could compare our periodic table with possibly another civilization's is one of the hallmarks of being able to have a common thing that we could communicate with. So this is chapter 7, and we want to be able to calculate the effective nuclear charge for atoms and ions, use the atomic model to explain periodic trends, including but not limited to atom size, electron affinity, and ionization energy. The first thing you have here is Mendeleev's periodic table. This was the first attempt to organize the elements by properties, and Mendeleev himself organized them by mass. He saw a similarity whenever chemical properties lined up according to mass, and he left gaps to predict future elements. So this is the first real attempt to organize the elements in any sort of systematic way. And it actually was a very good job, but it turns out that it's not the best way. In 1913, Thomson found evidence for isotopes. And what he did was an extension of the Thomson experiment, different Thomson. But what they did is they fired atoms between charged plates. And whenever they fired atoms between charged plates, you expect them to curve along a certain path. So all of carbon dioxide goes one way, all of carbon monoxide goes one way. But the interesting thing about this was when they did it for neon, there were two distinct lines. There was one that was here, and there was one that was here. And so the question is, why were there two distinct lines? And the evidence was, well, the only way that this would happen is they were exposed to the same charge, they were fired with the same velocity. The only explanation would be that maybe the neon has different mass. And so that was the evidence that they had that isotopes were the case. So here's the problem. You have an element of neon that has a very, very specific reactivity, and now it has different mass. So we come up with Moseley's periodic table. Moseley's periodic table, organized by atomic number, which is the number of protons. It's more consistent as far as lining up chemical reactivity than it was with atomic mass, so it's better in that respect as well. And then the vertical columns have similar chemical properties. It is important that you bookmark ptable.com. It is a quick reference for you to be able to say, okay, this is what I need to know about this element, this is the atomic mass of this element, this is the charge of this element, this is the electronegativity of this element, so it's a great tool for you to have. So whenever we look at the periodic table in the atom, we look at the proton and electron interaction. And atoms tend to be held together by the electrostatic force. That's the attraction between the positive protons and the negative electrons. Like we said, opposites attract. You have a positive charge and a negative charge, and they attract to one another, and that's what holds the atoms together. On kind of a side note, it's actually something called the strong nuclear force that actually holds the nucleus together. That's what keeps the positive charges together. It's actually stronger than the electrostatic force, but it acts over a very short distance. But it's this proton-electron interaction that keeps the atom together. And it does so by Coulomb's law. Coulomb's law we've talked about in first-year chemistry quite a bit. It's also referenced quite a bit in physics. But it is basically the idea that the electric force is equal to a constant times the two charges divided by the distance squared. And you see those right here. You see the electrostatic force is measured in newtons. You see the constant, you see the charge, you see the charge, and you see the distance. Now, you're not going to be expected to do a large amount of calculations using Coulomb's law. But we're going to go ahead and start off and expect you to do some, because understanding the conceptual part of Coulomb's law is really key to understanding chemical properties. So, it says determine the attractive force between a proton and an electron at Bohr's radius, which is 5.29 times 10 to the minus 11th. So we want to use Coulomb's law in order to accomplish this. So when we do that, hold on just 1 second. I'm trying to pull up a calculator. We know that the equation is F is equal to K Q1 Q2 over D squared. Now we've actually talked about this, and you can look it up on a periodic table what the charge of a proton and an electron are. The charge of a proton is 1.6 times 10 to the minus 19th, which makes the charge of an electron 1.6 times 10 to the minus 19th, but negative. So they have the same magnitude, they just have different charges. So the K value, if you were to look on the previous page, tells you that that is 8.99 times 10 to the 19th. multiplied by 1.6 times 10 to the minus 19th multiplied by negative 1.6 times 10 to the minus 19th. And you may have concerns at this point. You say, well, wait a second, that means I'm going to have a negative force. Those of you who are familiar with Coulomb's law know that when you have a negative force, it simply means that it's attractive. Okay, if you have a positive force, it actually means it's repulsive, but we're not going to have that between a proton and an electron. Okay, then we would divide this by the radius, which is 5.29 times 10 to the minus 11th squared. So we plug it into our calculator, 8.99, and then you'd use your E button, 9, times 1.6, E negative 19, and then enter, and do it again, and then divide by 5.29, E minus 11, and when you do that, you got to do that twice, and you end up with a fairly small value. Okay, you end up with something like, hold on a second, something like this is 10 to the 9th, 2.72 times 10 to the minus 29th newtons. Okay, next it said, how would it be difficult to calculate the net force between protons and electrons in helium? This is a conceptual question, and the reason why is, here's my positive charge. So we're going to kind of neglect the fact that there are two positive charges and just treat it as one. So you have 2Q, and it's positive. The problem now is that you have Q, which is negative, and Q, which is negative. So you would have to take into account the attraction here, the attraction here, and the repulsion here, and the repulsion there. So it starts to be very difficult mathematically, even for something as simple as helium. Now take into account the fact that these charges right here move relative to this, and the calculation gets extremely difficult. So that's why, one of the reasons why the Bohr model, or the classical model of the atom, Bohr is based on this idea of Coulomb's law, fails once you get past the past one electron. Now, we have something that's called effective nuclear charge. Coulomb's law, we just showed you, is tough for helium. Imagine trying to do it for uranium. Okay, this electron is attracted, but then it's repulsed by this one, and then it's repulsed by this one, and it's repulsed by all the other 91 electrons other than itself. So Coulomb's law can be extremely difficult. There's no way that you could get a reasonable approximation for the force of an electron and a proton on each other for a 92 electron atom. You just couldn't do it. So instead what we do is we talk about something called the effective nuclear charge. The effective nuclear charge allows us to estimate the average attractive force. So it's real key that you understand that it's an estimate, but it is a very, very, very good estimate, and it actually helps us explain all of the patterns that we see in terms of the periodic table. So it's a very good estimate, but it is by no means exact. And then it's an average attractive force. This electron will move closer to the proton, and it will be further away. So it's just taking the estimate of a snapshot and kind of putting it all together. Now, to calculate the effective nuclear charge, you use this formula. This formula is very, very simple. Z effective, that stands for the effective nuclear charge, is equal to the atomic number. This is the number of protons, and then we subtract the number of what we call shielding electrons. Another way of shielding electrons is if you think of inner electrons. Okay, so we've talked about valence electrons before. Remember, valence electrons are the ones that are on the outermost level. So if I've got two electrons here, this right here is a valence electron because it's in the outermost level. These two electrons right here would be considered to be inner electrons. Okay, so that's how we calculate the effective nuclear charge. You just take the number of protons and you subtract the number of inner electrons. So it says calculate the effective nuclear charge of bromine. So to calculate the effective nuclear charge of bromine, we're going to use the equation. Hold on just one second. Z effective is equal to Z minus S. And so we have bromine. Bromine, if you look at the periodic table, has an atomic number of 35, which means it has 35 inner protons. 35 protons. Now we have to subtract the number of shielding electrons. Now the number of shielding electrons can easily be calculated on the periodic table if you just look at it. Okay, So you find bromine's position on the periodic table, and it's roughly right here. It's a halogen, and it's in the 4th period. So now what you need to do is, in order to figure out the number of shielding electrons, you go backwards until you get to a noble gas. So the noble gas that I would get related to bromine would be argon. Okay, it's not krypton. Even though krypton's right next to it, you have to go left. So if you were to look at argon, argon has 18 electrons. So whenever you have a complete orbital shell, like in a noble gas, that references the number of shielding electrons. So if you were to draw bromine, what you would have is you'd have 2 electrons, 8 electrons, 18 electron, a total of 18 electrons. Once you got to that point right here, now we're talking about these electrons are we're talking about. That's what we're trying to find the effective nuclear charge for. The valence electrons. What's the effective nuclear charge? Because although I have an electron right here and it's attracted to this nucleus, all these other electrons are in the way. And so those electrons could repel or be on the other side and repel. And so it's taking the average of that. So the effective nuclear charge for bromine in this case would be 17. Electron shielding. So the valence electrons do not experience the full attraction of the nucleus. So that's the whole idea, that this electron right here does not experience the same 12Q positive charge because it's got 1, 2, 3, 4, 5 electrons that are kind of in the way. So that's the reason why we have this effective nuclear charge instead of just calculating the charge of the nucleus itself. There are definite trends for the effective nuclear charge. Okay, if you were to look here, this is a bar graph that represents the atomic number and the effective nuclear charge. So if you look, the atomic number increases by 1 each time because we're going up the periodic table. So you see this steady trend. And you start to see an increase there, but then it drops off all of a sudden. Okay, so all of a sudden the effective nuclear charge increases and then it drops. It increases, 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 it drops. It increase, 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 and then you could probably guess what it's going to do next. And the answer is, each time it gets to a noble gas, the very next element drops significantly. Okay, so if you were to look, the effective nuclear charge that we have for hydrogen is there are no shielding electrons, so it's 1. For helium, there are no shielding electrons, so it's 2. Once we get to lithium, the atomic number is 3, but now I have 2 shielding electrons, so it gets to be 1. I have beryllium is 4, but there are still only 2 shielding electrons. There's only 2 shielding electrons all the way until I get past neon. Once I get past neon, there are now 10 inner shielding electrons. So we have periodic trends. So the effective nuclear charge increases from left to right and increases from top to bottom. So this is a key AP idea. The properties of atoms can generally be explained by the combination of effective nuclear charge and Coulomb's law. So we're going to say, remember to clench. That's your key AP idea. If I had to say, if there's 5 ideas that you have to know going into the AP exam, this is number 1. Because it's going to explain a lot of the things that you see later. The idea of what's the effective nuclear charge, opposites attract, likes repel. This can be one of the things that makes or breaks you on the AP exam, so you need to make sure that you understand the idea of effective nuclear charge and how it relates to Coulomb's law. Next we have classical atom size. It's really hard to define what an atom is because the electrons are always in motion. We like to draw them in these nice orbital kind of pictures, but remember, electrons can be treated as waves, and they can really be anywhere. 90% of the time it's here, but these electrons are in waves, and these waves kind of move, and it could be over here. So it's really hard to define the classical atom size. Traditionally, the classical atom size has been, okay, if I have 2 of these atoms that are next to each other, what is half of the distance between the nucleus? That's generally how they define the classical atom size. That's also referred to as the non-bonding atomic radius. Okay, so we have some things with that. You can estimate the bond length for certain things based on the idea of effective nuclear charge. Here's a couple of estimates that you have here in terms of picometers. And like I said, it's the sum of, hey, if I have 2 hydrogens, okay, if I have two hydrogens together, that's the distance between the two of them. So if I was looking at what the bond length of this, or what this hydrogen would be, I take it divided by 2, and that would be the size of a hydrogen atom. Quantum size. Whenever you look at an atom in terms of a quantum atom, there is no defined boundary. The electron can be anywhere. I mean, this is the atom, the nucleus is right here. Most of the time the electrons are here, but the electrons can be all the way in Thailand for some reason. Okay, so because of that, you can't really define a quantum atom size. Instead, what you do is you talk about an atom in terms of probabilities, and in which case the electron probabilities must equal 1, because the electron has to be somewhere in relation to that atom. Atomic radii. So the atomic radii increases as you move down the periodic table, and it increases from right to left. So it's kind of an interesting pattern that you've got there. So we're going to look at that in terms of Coulomb's law. If you look at atomic radii in the CLENCH, more protons equals a greater attraction to the nucleus. Okay, a lot of times when we talk about atomic radii, we talk about the isoelectronic species. Isoelectronic species are atoms that have the exact same number of electrons but varying number of protons. Okay, and so here's the example that we have here. The example that we have here is O2 minus, F minus, neon, Na plus, and Mg2 plus. Okay, those are isoelectronic species because they all contain the same number of electrons. Neon has 10 electrons and 10 protons. Okay, fluorine has 9 protons and 10 electrons because it's F minus. O2 minus has 10 electrons and 8 protons. Sodium has 10 electrons and it has 11 protons. Magnesium has 12 protons and once again it has 10 electrons. Now if you were to look at the relative attraction between these two, remember the more charge there is, the more they're attracted to one another. So if you have 8p and 10e, there's not a very big attraction between those two, so because of that the atom tends to be larger. Okay, whenever you have fluorine, you're adding more positive charge, so it's going to pull these 10 electrons in closer, but still not that much. When you get to the idea that you have 12 protons attracting these 10 electrons, it's going to make a significant difference in shrinking that atom. Okay, atomic radii, more electrons equals a greater attraction, and therefore a smaller radius, unless another level is added. So once again, it brings up the whole idea of if I have let's say I have oxygen, and if I just have regular oxygen, and I have neon, and I have fluorine, okay, oxygen or neon's got 10, fluorine's got 9, oxygen has 8 because they're not ions anymore. Okay, 8 protons, 8 electrons, 9 protons, 9 electrons, 10 protons, 10 electrons. The attraction between these two is going to be much, much greater than it is between these two, than it is between these two. So because of that, oxygen tends to be larger. Now, once you get to the fact that you get to the next level up, which is sodium, and you say 11 and 11, they say, well, sodium's got to be smaller then because that's going to be an even greater pull. And it's not, because at this point, oxygen, fluorine, and neon work on 2 orbitals. This orbital and then this orbital. When you get to sodium, you're adding a 3rd orbital. When you add that 3rd orbital, you're greatly increasing the atomic radii because you're significantly increasing the distance away at that point. Ionic radii, generally ionic radii is determined by comparison with the electric crowd it emulates. So if you were to look at lithium, you would compare lithium to helium. Now the difference is that helium has 3 protons and 2 electrons because it's an ion, and this one has 2 protons and 2 electrons. So if you were to look at this, you would say that this would have a greater attraction than this, and therefore the lithium ion, although it's very similar in size to helium, is going to be slightly smaller because it's going to have a greater attraction. So now we need to talk about the idea of ionization energy. We've already explained atomic radii and ionic radii in terms of Coulomb's law and effective nuclear charge, but now we need to look at the idea of ionization energy. Now, just as a review, ionization energy is the energy that's required to remove an electron from an atom completely. So it depends on the positive charges, the negative charges, and the distance between. In other words, it depends on Coulomb's law. And it's interesting that you see a very similar pattern to effective nuclear charge as you see with ionization energy. So if you were to look, this is the ionization energy of hydrogen. This is the ionization energy of helium. And then so it goes up, and then you see a very significant drop. Lithium drops way down. Then you see an increase. You see an increase, kind of a little drop right there, and we can talk about those drops in just a second. But a general increase and then a drop, a general increase and then a drop, a general increase and then a drop, which is very, very similar to what you see for effective nuclear charge. Now let's talk about why. If you were to look at it in terms of effective nuclear charge, the reason why you see such a precipitous drop is you are going from helium, where you've got 2 electrons, and the effective nuclear charge is 2, you're adding a significant amount by adding a 3rd electron. Yes, the effective nuclear charge goes from 2 to 1, so we are decreasing the overall pull because of the charge, but you're also, look at this big difference in distance. The difference in distance is you're increasing the distance. Now remember, Coulomb's law says that the force that attracts the two is equal to Q1, Q2 over d squared. So any change in the distance is going to have a dramatic impact on the amount of energy or force required to pull something apart. And you can start to see these in the trends. Now, this makes its way in terms of ionization energy. You can see that you can ionize something multiple times. And you can see this right here. This is a big question that you tend to see on the AP exam because there tend to be questions about data, and they show this data to ask questions about. So you see the element, you see the energy for the first, second, third, fourth, fifth, sixth, and seventh ionization energies. Now the general thing that you would expect to see is as you remove an electron, you make it more difficult to remove another electron. Okay, and that just has to do with the fact that whenever you remove an electron, it's going to have the opportunity to shrink just a little bit, and so it's going to be more difficult to remove that second one. So the general idea is that you would see an increase in the energy, and you definitely see that for sodium. Look at that giant increase between the first and the second. But now, if you were to look at magnesium, you see a much smaller increase with the second one, and then a giant increase with the third one. For aluminum, you see a slow increase for the first, second, and third, and then you see a giant increase for the fourth. Well, let's try and explain why. If you were to look at sodium, you have your positive nucleus, you have the first orbital, which has 1, 2 electrons in it, you have the second orbital, which has 1, 2, 3, 4, 5, 6, 7, 8 electrons in it, and then you have the third orbital, which has 1 electron in it. So the amount of energy required to remove the first electron is that 496. So I take that first electron out, and now what I'm doing is I'm having to move to an inner orbital where these electrons are not only have a high effective nuclear charge, okay, the effective nuclear charge is as high as it can be, but also they are much closer than this original electron because I'm going from the third energy level to the second one. Removing one from the third energy level is much easier than removing one from the second. So now, let's look at it for another element. If you were to look at it for magnesium, magnesium originally starts off with 2 electrons in its outermost energy level. So removing the first one is relatively easy. Removing the second one is relatively easy. But then I'm trying to, once again, remove an electron from the inner orbital level. And that tends to be very, very difficult. So you see this pattern continue. First one, second one, third one, fourth one, all of these are in the 3s orbital, but when I jump up to that fourth orbital, that's where it gets very, very difficult. So the first ionization energy trends, ionization energy decreases as you move down the periodic table. The reason why it decreases as you move down the periodic table is, as you move down the periodic table, you're adding layers or increasing the distance that you're moving away from the atom. Okay, generally, ionization energy increases as you move across the periodic table. The reason why it increases as you move across the periodic table is the effective nuclear charge is increasing. So the effective nuclear charge starts at 1 and then goes to 2 and then 3 and then 4 and then 5. So it takes more energy to pull them away because they're more attracted to another at that point. Electronegativity is the ability of an atom to capture an electron. to gain access to the positive nucleus. And once again, it depends on the same things that we're talking about in terms of Coulomb's law and effective nuclear charge. Electron affinity is the same thing. It's the measure of an attraction for an electron. It's the amount of energy released as an electron is added. And so once again, it's the whole idea of what is the pattern between Coulomb's law and effective nuclear charge and electron affinity. Okay, we tend to deal with electron negativity whenever we're talking about bonding, and electron affinity whenever we're whenever we're referring to an atom by itself obtaining an electron, so ionization, those sorts of things. So electronegativity increases as you move down the periodic table. Okay, so we see increasing this should say as you move up the periodic table. Okay, electronegativity goes up as you go this way, and electronegativity increases as you go to the right. And the reason why is you're talking about access to the positive nucleus. Okay, that's what's happening. So for electronegativity, you're trying to bring an electron in. Well, as you go up the periodic table, here's my positive nucleus. Well, if I have, let's say, 3 orbitals, okay, if I have 3 orbitals, it's very difficult for an electron here to access the positive nucleus. But if I were to take this orbital away, well, now it's a whole lot easier because I've only got 2 orbitals to deal with. And if I were to go here, now it's a lot easier because I only have 1 orbital to deal with. So as you go up this table right here, you're increasing the electronegativity because you have better access to the positive nucleus. Now, as you move across the periodic table, you're increasing the positive charges that are in the nucleus. The positive charges are going to have a greater impact on this electron right here because the bigger the positive charge, the more electrons are going to be attracted to it because you are increasing the effective nuclear charge. Now this trend excludes noble gases. Noble gases, remember, are perfectly satisfied. So when we say it increases from left to right, it does so excluding the noble gases. Here's an example. It says, this is a tough one. It says, under what circumstances might helium have a greater electronegativity than fluorine? And you look at fluorine as the most electronegative of all the elements. And the reason why it is because it has a positive charge, and it has only 2 levels, and it has 1, 2, 3, 4, 5, 6, 7, and let's add the s orbital there, 8, 9. It's got 9 electrons. So it has an effective nuclear charge of 9 minus 2, which is 7. That's an extremely high effective nuclear charge. It only has 2 orbitals to contend with. So it has access to a very, very positive nucleus. And so that's what makes it have the greatest electronegativity. So the question is how could I make it so that helium has a greater electronegativity than fluorine? And the only way that I can think of is if you remove an electron. If you had helium that had a +1 or even a +2, the effective nuclear charge of helium would be 2. Okay, so the effective nuclear charge is smaller, yes, but the effective nuclear charge of helium is greatly helped by the fact that it only has 1 orbital. Not only does it only have 1 orbital, but it only has 1 electron that could possibly interfere with an external electron. So the only way that you're going to have a greater electronegativity than fluorine for helium is if that helium is an ion. And helium is very, very difficult to ionize. Next it says, describe why magnesium and copper have the same atomic radius. Okay, remember, atomic radius is determined by CLENCH, Coulomb's law, and effective nuclear charge. So if you wanted to look at this, you have to look at their relative positions on the periodic table. So the first thing you want to look at is, where is magnesium and where is copper on the periodic table? So let's pull up our periodic table, and when we do that, we see that magnesium is 3s2, so which means that it has 10 shielding electrons, and it has 12 is the atomic number. So the effective nuclear charge is 2, and it has 3 orbitals to contend with. Okay. Copper, on the other hand, copper, if you were to look at it, is in the 4th column, and it has, once again, it's got 18 shielding electrons, but it has an effective nuclear charge of 11. So that right there shows that copper has a greater effective nuclear charge. So there's a greater positive pull on a valence electron. But magnesium has 3 energy levels. Copper has 4. So even though this one has 3 energy levels, those energy levels are relatively spread out because the effective nuclear charge is fairly small at positive 2. Copper, on the other hand, has 4 orbitals, 2, 3, 4, that are relatively spaced together because of its rather high effective nuclear charge of 11. So they're not the exact same, but it shows you how two elements could have approximately the same atomic radius, even though they're in very different periods and very different rows. Periodic trends. Only the noble gases are found as monatomic atoms in nature. Elements are divided into nonmetals, metals, and metalloids. Now, generally speaking, we refer to metalloids as these stair-step ones, starting with aluminum and working our way diagonally across the periodic table. Those tend to be things like our semiconductors. Nonmetals are to the right of the stair-step, metals are to the left. The only one that's weird is hydrogen. Okay, when you look at the periodic table, depending on what you're looking at, sometimes helium should be here because it's an s orbital. Sometimes hydrogen should be here because it's a nonmetal. They're the only two ones that are weird. Everything else, metals to the left, nonmetals to the right. Properties of metals: they conduct heat, they conduct electricity, they're malleable, which means they can be pounded into thin sheets. They're ductile, which means they can be drawn into thin wires. They're solids at room temperature. They are very, very easy to ionize. They form cations when they do, which means that they are positive metal ions, and they form ionic bonds with nonmetals. They tend to be basic, so if you were to add them to acids, they tend to neutralize them. Okay. On the other hand, you have nonmetals. They don't conduct heat. They don't conduct electricity. They tend to be gases at room temperature. Some of the bigger ones are liquids. They have high ionization energy. It's very difficult to remove one because their effective nuclear charge is much higher. They form anions, which are negative. They form ionic bonds with metals, and they form covalent bonds with each other. Okay, they're nonmetals and they tend to be acids. The metals themselves, they can form what are called metallic bonds with each other, which are very, very different than the covalent bonds that are formed with nonmetals. Metalloids are somewhere between the metals and nonmetals in all properties. That's why they tend to be semiconductors in heat, semiconductors in electricity, those sorts of things. Alkali metals, you see, are group 1. They're soft, metallic, lustrous, and they're very reactive. Alkaline earth metals, group 2, soft, metallic, dull, reactive. Transition metals, group 3s, hard, metallic, lustrous. They tend to make colored solutions, like copper makes blue or green, depending on what it's paired with, and iron is red or orange. They tend to be conductors. Halogens you have. Halogens are obviously nonmetals. They're group 17. They tend to be gases at room temperature, except for I think this last one right here is not. Oh, and bromine tends to be a liquid. They're highly reactive with nonmetals, and they're very, very lethal to organisms. Noble gases, non-reactive gases. So what element in halogens has the largest atomic radius? So if you look at this by saying halogens, we've limited it to this particular column. So which element has the largest atomic radius? If you're in the same column, they all have the same effective nuclear charge. So because of that, you would look at the one that's the lowest on the periodic table because it would have the most layers, and the one that has the most layers is At. So that would be our largest atomic radius. Which elements would have the same chemical properties of calcium? If you were to look at calcium, calcium is in group 2 of the periodic table. So you can name anything in group 2 of the periodic table, which would include beryllium, magnesium, strontium, barium, radium. The ones that are closer to calcium would tend to be more similar, so those would be magnesium and strontium. When you get really small or really big, sometimes they react much more strongly or much less strongly based on effective nuclear charge.